Hello there, Mr. Sutton here, bringing you the Algebra 2 Honors 11.5 lesson on using recursive rules with sequences. In this one, we will be writing terms of recursively defined sequences, we'll be writing recursive rules for sequences, and we'll be converting between explicit and recursive definitions of sequences. So stay tuned for this two-parter. So we'll begin our discussion of recursion by getting the lay of the theoretical land. The first thing we're actually going to talk about is not recursion, but something called an explicit rule. So an explicit rule for a sequence gives your a sub n as a function of the index number, the n. And we've actually been using this entire time. You tell me the index number, and I plug that directly into some function, and it tells me the value of that item in the sequence. So that's one way of doing things. A totally different way of thinking about things is something called recursion. With a recursive rule, you're going to be giving back an a sub n as a function of the previous terms. So you need to tell me one term, and then I can tell you the next term by applying some rule to it, some recursive rule. Now, of course, if you try to backtrace this all the way to the beginning, you need to start somewhere. So we have a first term or base case already defined to go hand in hand with whatever recursive rule we're dealing with. So just to give you kind of a flavor of the difference between these two rules, let's take a look at some explicit rules for arithmetic and geometric sequences and see how the recursive rule compares to those. So I made a little chart here. The arithmetic explicit rule, you might remember this one, that's a sub n equals a sub 1 plus d times n minus 1. With a recursive rule, instead of starting with this first term and then adding, the common difference times the number of terms minus 1, with a recursive rule, you're starting with the last term. That's a sub n minus 1. This is the term right before the one you're looking for. And then, well, with an arithmetic rule, you just keep adding the same thing over and over, this common difference. So the recursive rule is just a sub n minus 1 plus d. So it's a little bit more simple and elegant and just gets you the next term in the sequence. And we didn't write it here, but again, you need a base case defined somewhere. So we would say a sub 1 equals some number that we're starting with. Now, geometric rule, the explicit one for that, we have a sub n equals a sub 1 times r to the n minus 1. So we have this common ratio that we're multiplying by. The recursive version of that, since with a geometric series you just keep multiplying by the same number over and over again, we're going to take that number, r, and we're just going to multiply it by the last term, a sub n minus 1. And this is the recursive version of a geometric series. So you might wonder, what are the pros and cons of each of these? The recursive sequence is kind of neat if all you want is the next term and you just want to keep generating next terms. These tend to be a little bit simpler and more elegant than the explicit version. At the same time, the explicit version can get you where you want to go a lot faster, at least if you're a human being. Like if I want to know the 1,000th term of some arithmetic or geometric series, I can just plug 1,000 in for n with whatever else is already there, and I'm there, just like that. With a recursive rule, if you want to know the 1,000th term, well, you need to first know the 999th term. And to know that, you need to first know the 998th term, and all the way back down to a sub 1. So that could take a while for a human, although computers can kind of do that in the blink of an eye. So you might wonder, like, if you're a human, why do you care about recursion? A couple of other reasons you might care about it. So it's huge in computer programming. A lot of computer functions call themselves and just keep backtracing to a base case, so knowing about this way of thinking is kind of important. Life is a recursive process. At any point in life, you're starting with the information that you have and doing something with that information to take the next step. And last but not least, there are some series out there, some sequences I should say, that can only be defined with a recursive function. There is no explicit function for them. The most famous of these is the Fibonacci sequence. So this is a sequence that it's a special kind of sequence. It has not one, but two base cases. A sub 1 is 1, and a sub 2 is also 1. Now, what do we do with the terms to get the next term in the Fibonacci sequence? So the idea here, here's our recursive equation for this one, is that you have to take the second to last and the last terms, the last two terms in other words, and add them together. So if we were to write out the Fibonacci sequence, we would have the 1 for the base case, the 1 for the other base case, and then adding the last two terms, 1 plus 1 gives me 2. And then for the next term, add the last two terms, 1 plus 2 is 3, and then 2 plus 3 is 5. And just take a quick pause on this and see if you can figure out the next few terms. All right, so 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, and you could keep going. Look at you generating Fibonacci numbers. Now, why do we care about the Fibonacci sequence? Well, it turns out this one shows up in a whole bunch of places you would never expect. It shows up in nature, finance, computer programming, even architecture, and music. So lots of places. Just do a quick AI search and ask, why are Fibonacci numbers important? And you will get a huge printout of everything they do. In fact, let me show you. So I actually asked Copilot here why Fibonacci numbers matter, and it tells me about flower petals, tree branching, computer search algorithms, data modeling, finance, market psychology, cryptography, architecture, and it even lets you approximate miles to kilometers, do that little conversion. Like a 3K or a 3-mile run is actually a 5K. Picture that. So lots of cool places. And there's no explicit function for the Fibonacci sequence, only recursive. So hopefully at this point I've convinced you of the value of learning about recursion, because otherwise that's like 6 minutes we're never getting back. But here is a few ways to use recursion now. We're going to dive into some examples. So for this first example, we are being asked to write the first 6 terms of each of these sequences. Each of these is a recursive sequence. It has a base case and also the recursive part of it. So the basic idea with all of these is just start with your first term and keep applying the recursive rule until you have the desired number of terms. And the first term counts as one of your 6, so you kind of got one for free. So pause the video and try each of these out, and we'll bring it back and see where you got. All right, so for this first one, again, we get that first term for free. We've got a 1. And now to get a sub 1, we need to do a sub 0 plus 4. We saw that a sub 0 was 1, so that's 1 plus 4, which is 5. To get a sub 2, we need a1 plus 4. So that's going to be 5 plus 4, which is 9. And then a3, that's a2 plus 4. So that's 9 plus 4, which is 13. a4 is going to be a3 plus 4. So that is 13 plus 4, which is 17. And then finally, a sub 5, which is actually term number 6 in this one. That's a4 plus 4. So 17 plus 4 gives us 21. And now let's do this other one here. We've got a base case of f of 1 equals 1 and f of n equals 3 times the last term. So we already got f of 1, that's 1. F of 2 is going to be 3 times f of 1. So 3 times 1, which is 3. F of 3 is going to be 3 times f of 2. So that's 3 times 3, which is 9. F of 4 is 3 times f of 3. So 3 times 9 is 27. And then f of 5, that's going to be 3 times f of 4, so 3 times 27, which is 81. And finally, f of 6, 3 times f of 5, which is 3 times 81, so 243. For the next couple of examples, we're going to be trying to write recursive rules for sequences, kind of like back in the day when we wrote explicit rules for sequences, although we didn't call it that, we just asked for the nth term. So basic idea with writing a recursive rule, you've got 2 parts you need for this. You need to explicitly identify your a sub 1. You need a base case, because otherwise you just infinitely recurse backwards and never actually get a number to plug in anywhere. We also need to then write the recursive rule that gives us the next step if you have the last term. And this can be a little bit tricky sometimes, so just as a little bit of a general hint, it's a good idea to see if you can use an arithmetic or geometric rule when you first look at a sequence. Take the most common sequences and see if it's one of those, because we've already got predefined sort of recursive formulas for arithmetic and geometric rules. So look for common differences and common ratios. With all that in mind, pause the video and try to write a recursive rule for each of these sequences and then test it out to see if it actually works. Alright, so let's take a look at this first one. Now I notice that 3 to 13 to 23 to 33, it looks like we keep adding the same number over and over again. We've got a common difference. So this is an arithmetic sequence, which means I can use my arithmetic recursive formula, which again was a sub n minus 1 plus d. Just keep adding the common difference. So remember also we have to write out our a1. So for this sequence, our first term is 3. That's where we get started. And then all we have to do is keep adding the common difference. So just subtract any pair of terms to find that. 13 minus 3 is 10. So we can write that a sub n equals a sub n minus 1 plus 10. And that's it. And if you test this out, if I want to find, a sub 2, that would just be a sub 1 plus 10, so that would give me 13. A sub 3 would be a sub 2 plus 10. 13 plus 10 gives me 23. So it works. You can very quickly see that these work. All right, now looking at this next one. This is definitely not an arithmetic series. We're not adding the same thing over and over again, but you might notice that it looks like we're kind of multiplying by the same thing over and over again. Like 40 times 2.5 is 100, times 2.5 is 250. So this is a geometric sequence, which means I can use my geometric recursive formula, r times a sub n minus 1. The r value in this case, let's just divide two terms to get that. 40 over 16, and there's our a1 by the way, 16. 40 over 16, or if you want to do 250 over 100, that might be easier. In any case, that's going to give us 5 over 2. So putting this all together then, we've got 5 over 2 times a sub n minus 1. Again, with that base case of 16. So we're going to get a little bit more practice with writing recursive rules for sequences, and I call this oddball sequences because these are not going to be arithmetic or geometric sequences, although it's worth looking to see just to start it off here. So this first one, if you're looking for a common difference, we've got -7, -2, -5, so clearly there's not a common difference here. And also common ratio, 9 over 16 is definitely not the same as 7 over 9 or 2 over 7. So, none of those rules are going to work here. So another common thing that you can try when those two rules don't work is to see if the two previous terms are being used together to generate the next term. Kind of like with the Fibonacci series we saw earlier, we were adding the last two terms to get the next term. If this is the case and you have to use the last two terms together, then just like the Fibonacci sequence, you're going to need two first terms, two base cases to start it off. So with that little hint in mind, pause the video and see if you can come up with a rule for example 3 here. Alright, so let's just look at the last two terms and see how those give us the next term. So how can I get a 7 out of 16 minus 9? I can't add 16 and 9 or multiply 16 or divide 16 and 9 to get a 7. However, 16 minus 9 is 7. So that's something. It could just be a coincidence though. Let's see if that rule works for the next two. So 9 minus 7 is that 2? Sure is. How about 7 minus 2? Yup, that's 5. So we could keep going with this, but it looks like this is what's going on here, is we're doing the second to last term minus the last term, and that gives us the next term. So we have to write our two base cases for that. That's part of the solution. So a sub 1 will be 16, a sub 2 will be 9. Those are required. And then we can write a sub n equals a sub n minus 2 minus a sub n minus 1. So it's kind of like a negative version of the Fibonacci. All right, So let's take a look at this next example, example 4, 1, 1, 2, 6, 24. Let's go through our list of usual suspects. Is it arithmetic? Nope. 1 minus 1 is 0, 2 minus 1 is 1, so already that pattern breaks down. Is it geometric? Well, 1 times 1 is 1, but we can't multiply by 1 again to get 2, so it's not geometric. Is it one of these Fibonacci sort of series? 1 plus 1 is 2, so it actually works for that first one. But 1 plus 2 is not 6, and 2 plus 6 is not 24. And if we're multiplying the last two terms together, 1 times 1 is not 2, so that already doesn't work. None of these other things we could do with the previous two terms is going to generate the next term. So there is one more little trick in the bag that I'm going to show you for this lesson, and that is, and this is not one you might think of because you're just kind of focused on, the terms themselves, but it's always worth checking, if none of this other stuff works, to see if the index numbers themselves are being used with the previous terms. So we've got index numbers of 1, 2, 3, 4, 5. Are those index numbers being used in some way? Is n being used in some way with a sub n minus 1 to generate the next term? So with that hint in mind, pause the video and see if you can come up with a recursive formula for this one. All right. So this first term has an index of 1. 1 plus 1 or 1 minus 1 or 1 divided by 1, well, 1 divided by 1 will give you 1, but that doesn't work for this next one. 1 times 1 is 1, however. And this second term, which has an index of 2, 1 times the index 2 equals 2. So that's an interesting coincidence. And then 2 times the index of 3 equals 6. Will it work again? 6 times an index of 4 equals 24. So yeah, we're just multiplying the last index number by the last term to get the next term. So we have our base case of, we just need 1 in this case, just 1 here. But then our recursive formula, we're going to have n minus 1, that's the index of the last term, times the last term, a sub n minus 1. And that's what we needed for this one. So this concludes the first part of our lesson on recursive sequences. Pause the video and try out some of these problems with writing terms and coming up with some weird rules. And then when we come back, we'll talk a little bit more about converting between explicit and recursive formulas, and also some real-life applications of these things. Welcome back. You're joining us for part 2 of our lesson on recursive sequences. So we're going to start this one off with a problem where we're trying to convert some explicit rules into recursive rules. And you've actually got just about everything you need to make this happen. Just remember, again, with your recursive rule, you need a base case and a recursive equation that gives you the next step. So pause the video and try to get a rule for each of these two explicit rules. All right, so for this first one, it's helpful to know that this is an arithmetic sequence, and we know that because it is linear. So that tells us this is arithmetic. And our arithmetic recursive rule, again, that was going to be a sub n minus 1 plus d. So that's the format that our recursive equation is going to have to take. We do need to get the a1 out of this, and that's pretty easy. We just have to plug 1 in for n in the expression they've given us. So negative 6 plus 8 times 1 comes out to an a1 of 2. And now for the rule, we just need to add the common difference to a sub n minus 1. What's the common difference from this arithmetic rule? Well, the common difference is just going to be this slope here. You just keep adding 8 over and over again for however many terms you're going, and that gives you the next term. So we can then write our recursive rule as a sub n equals a sub n minus 1 plus 8. All right, let's take a look at part B now. This one, because of the exponential term, you might recognize that this is a geometric sequence. So the recursive geometric formula, again, that was r times a sub n minus 1. And we do need, again, to get the a sub 1 out of this. So just plug in 1 for n in the formula that they've given us. 1 minus 1 is 0. 1 half to the 0 is 1. So that just gives us an a sub 1 of negative 3. Okay? And now to get the recursive rule, we just need to figure out the r value from this. Now remember, r is what you keep multiplying by over and over again. That's going to be the base of your exponential piece here. So the r in this one is going to be this 1 half. So our a sub n is going to be 1 half times a of n sub 1. For this next set of problems, we're now starting with a recursive rule and trying to convert that into an explicit rule. So here are two different recursive sequences. Pause the video and try to come up with an explicit rule for these. All right, for this first one, since we're subtracting this 2 from the last term, this is just an arithmetic sequence, recursive style. So if we're going to write an explicit rule, it would be helpful to rewrite the explicit formula for an arithmetic sequence. Again, that was a sub n equals a sub 1 plus d times n minus 1. And as you might remember, to figure these out, we need to get an a1 and a d value and then simplify everything after plugging in. A sub 1 is pretty easy because they literally spelled it out for us. It's negative 5. So that's going to be negative a sub n equals negative 5 to start with. And now for the common difference, that's what you keep adding or subtracting over and over again. Our recursive equation is telling us that we keep subtracting 2. So our d value is going to be negative 2. And then we have that n minus 1 that's always there. Now remember, you do need to simplify this. So this is going to be negative 5 minus 2n plus 2. And then negative 5 and 2 gives us negative 3. So negative 2n minus 3. All right, so that's our arithmetic rule. Let's take a look at this next function. Now with this one, we keep multiplying by 2 over and over again to the last term. So this is a geometric recursive style sort of sequence. The explicit geometric formula again was a sub 1 times r to the n minus 1. So this is what we're trying to convert this into. A sub 1 is 10. Again, they gave us that, which was kind of nice. R is what I keep multiplying by, so that's the 2. We can pick that right out of the recursive formula, and that's just going to be 2 to the n minus 1. So that one's actually done. So at this point, we're going to do some practical applications of recursion. We'll start with this fishy problem here. A lake initially contains 5,200 fish. Each year, the population declines 30% due to fishing and other causes that we won't name. So the lake is restocked with 400 fish. So we've got a few things we want to do here. They want us to write a recursive rule for the number of fish, a sub n, at the start of the nth year. They also want us to find the number of fish at the start of the 5th year and describe what happens to the population of fish over time. So I'm going to have you pause the video and see if you can come up with a recursive rule for this part A, and then we'll do parts B and C together. So pause the video, give it a shot. Alright, so if I'm doing a recursive rule for number of fish at the start of the nth year, at the start of the 1st year, our lake initially contains 5,200 fish, so we can say a sub 1 equals 5,200. That's our base case. Now what's happening at the start of every subsequent year? Well, our population is declining 30%, so we have to incorporate that. How can I say losing 30%? Well, losing 30% basically means keeping 70%. So we need to take 70% of whatever the population is. That's going to be the a sub n minus 1. And then we'll have to do something else to it. So let's start there. So our a sub n is going to be 0.7. That's take 70% of a sub n minus 1. Now we're also restocking with 400 fish. So what are we doing with 400? We are adding it to the remaining total after this decline has happened. So there is our recursive function. For the next part of this, again, they want us to find the number of fish at the start of the 5th year. So this is something that you could do by hand. You could say, okay, what is a sub 5? Well, that's 0.7 times a sub 4 plus 400. Oh, wait, what's a sub 4? And we could keep working backwards until we get to this base case. Could totally do that by hand. But I did want to show you how to do recursive functions on the Desmos calculator. It turns out you cannot actually enter a recursive function in the scientific calculator, but you can do it in the graphing calculator. So the way that you would go about this is you can define and use recursive functions in our Desmos graphing calculator by defining your base case, which you're going to have to call f of 0 or f of 1, whichever you want to use, and defining your f of n function in two separate lines. So we need an entry for this 5,200. We're going to need another entry for this recursive equation. So let me pull up Desmos. All right, here we are. Now we're calling this A1, so in Desmos I'm going to enter that as f of 1 equals 5,200. So that gives me my base case. And for this other one, we're going to write f of n equals 0.7 times, now a sub n minus 1, I have to write that as f of n minus 1, so function version of this. And then I need that plus 400 there, plus 400 as well. And that gives me a recursive function. Now if we would just want to test it out on the first couple here, f of 1 should give us 5,200. Let's make sure that at least works. So there's f of 1. Here is f of 2. So this is what you would get if you multiply this by 0.7 and then add 400. So let's skip all the way to f of 5. And that's giving us about 2,262 if we round it off. So that's how many fish remain at the end of that, the beginning of the 5th year. And I'll just stick some units on there as well. So we can see that if you're able to use the graphing calculator, although the recursive approach is kind of slow to do by hand, graphing calculator can pump those out pretty quickly and give you some good information. Now let's take a look at this next one. Describe what happens to the population of fish over time. So they're basically asking, as you plug in bigger and bigger input values, what is happening to the total number of fish? So to do this, we would just plug in some increasingly higher values and see if the output levels off. So let's go back to Desmos, and we'll just start plugging in some higher numbers. So we can do 6, 7, 8, and we see that the total number of fish seems to be declining year after year. So we've got 10, and it keeps declining. If you want to speed this up a little bit, you can skip a few numbers. So let's do like 15, and then let's do 20. How about let's do 30? Let's do 40. And we see that once we've gotten like past 30, 40, this isn't changing a whole lot, but let's zoom forward several years. Let's do 100. And this is like 1,333.33. Can I add another 0 there without breaking Desmos? It looks like I can. Cool. So I think we could keep adding zeros, but it's pretty conclusive that this thing has leveled off at 1,333 fish. For our last problem, we're going to take a look at some finance here. Now, we had a chapter on exponential stuff, so you saw that there was lots of great, direct, explicit formulas for figuring out, how much interest you will have acquired over time or something like that. This is a little trickier, though. So we have a home buyer borrows $150,000 at 6% annual interest, compounded monthly for 30 years, and they're giving this monthly payment of $899.33. So there's multiple things going on, right? Because we've got the interest that's accruing every single month, but at the same time, we are also paying this thing down by a certain amount. This is a little bit too complex to capture with just an explicit formula, so recursion actually works really well in this case if you're trying to figure out what you're going to have for a balance after each payment. Specifically now, they want us to find the balance after the third payment. So pause the video, use what you know about interest and finance and all that and recursion, see if you can come up with a recursive formula for what we have after n payments, and then see if you can use it to find the third payment. All right, let's see how that went for you. So with a recursive rule, again, we need a base case and then a recursive equation. So for the base case, we're starting with $150,000. I'm going to call that A0, right? This is year 0, and then after the first payment, that we'll call that A sub 1. And now for the recursive piece of this, whatever my balance is, I have to multiply that by 1 plus the interest rate, and then I have to subtract this monthly payment. So I'm going to have 1 plus r times a sub n minus 1. That's 1 plus the interest rate times the current balance, the last balance, and then we're subtracting that monthly payment. Now what is this r value? Here we have to be a little bit more careful. This is annual interest, but we need monthly interest. So we're going to have to do 6 divided by 12 to get this particular r value in here. So 0.06 divided by 12, because it's a decimal that we're using. Let's go on Desmos and find that. So 0.06 divided by 12 gives us 0.005. So that's the r that we're using here. So plugging that back in, this is then going to be 1.005 times a sub n minus 1 minus 899.3. So this is our recursive equation. We're going to use this with our base case now in Desmos, then the graphing version, to figure out the balance after the third payment. So let's go back to Desmos. So here we are. Let me write out my base case. So f of 0, we're going to call that 150,000. And then for f of n, that's going to be our recursive rule. So 1.005 times f of n minus 1 minus our monthly payment of $899.33. And now we've got a recursive rule. So our balance after the first year, f of 1, that's $149,850.67. That seems reasonable. I mean, it doesn't seem like we've paid a whole lot down, but you have to remember we're having this interest accrue and then we're subtracting that monthly payment. So that interest is kind of the sticker there. So let's skip to f of 3. And that's going to be $149,549.77 if we round that off. 77. There we go. It's important to get it exactly right. Otherwise, the company that loaned us the money is probably going to start, going after our assets or something. All right. So that's part A. Part B, they say due to rounding in the calculations, we just talked about rounding, the last payment is often different than the original payment. Really? That's kind of interesting. They want us to find the amount of the last payment. So to do this, it would be helpful to first find the amount remaining after the second to last payment. So we're going to find the second to last balance first. So which term would that be? Well, since this is a 36-year loan and each payment is just 1 month, that means we have 30 times 12, 360 total payments. So the last payment is going to be payment number 359, or the second to last payment will be. So let me go back to Desmos and let me do f of 359. Now this would be incredibly obnoxious to do without this graphing utility here. Just doing this by hand, this is like 360 different lines of this stuff. But the calculator, 359, just does it just like that, like it's nothing. So this is $890.65. So that is approximately what our second to last balance is. So in order to get the last payment, we have to, again, multiply, using our recursive rule, we have to multiply this by 1.05005 and then subtract that 899.3. So let's go ahead and do that. And actually, we're not going to subtract the 899.33 because that would be our normal monthly payment, but this is the last month. So this is just going to be what we're paying for that final payout. So plugging this in the calculator, we'll go down to a new level here. 890.65 times 1.005. So our final payment is actually going to be $895.10. which you might notice is a little bit less than your regular monthly payment. So I guess we paid a little bit in advance with all those small roundings that were going off there. So that's it for our lesson on recursion. Hopefully we were able to pique your interest in this one. Till next time, Mr. Sutton signing off.